All right, so today we're going to start volumes. We probably won't do all of the notes that are in here because the last part is volumes by cylindrical shells, which you don't have to know tonight. Actually, you don't have to know ever. No, it makes certain problems easier.
Okay.
It's one where it's not required on the AP exam, but there are times when it does make things easier, and I there are things where I'm like, I would be negligent if I didn't teach you some things that aren't on the AP exam. So those are on there. So volumes. The basic idea is pretty simple, actually. I have fellow colleagues who spend, particularly with AB classes, like 2-3 weeks on just this one idea, and I'm like, it's not that complicated. Yes, but we built all these things out of Play-Doh, and and I'm like, no. Like, that's great, but does it really help them understand it better? Well, they can see it in 3 dimensions. I'm like, do they need to see it in 3 dimensions to do the problems? No? Okay. So the basic idea is this. If you know the cross-sectional area in terms of x, a of x, from x equals a to x equals b, then the integral of that area gives you the volume. Ta-da! That's the whole idea.
Oh. I don't get it.
I need some
Play-Doh.
Yeah.
I need some three-dimensional Play-Doh right now.
So basically what you have to be able to do is come up with a formula for the area of every cross-section. It's not as hard as it sounds.
It looks kind of bad.
So here are some typical cross sections. Most of these, you probably know these formulas very easily off the top of your head. Some of them, you may not. Particularly,
Equilateral.
you may have forgotten this one because it doesn't get used a whole lot, but
Square.
all of you except for Lynn were in my honors geometry class. We did that formula. Whether you remember it or not is immaterial. We did this formula. Side squared times the square root of 3 over 4 for the area of an equilateral triangle.
Sure we did.
Yeah. So cute.
A semicircle comes up fairly regularly.
How'd they get that? Where'd that come from?
And then an annulus. You're like, what the heck is an annulus?
Yeah.
Well,
Play-Doh? Play-Doh?
Play-Doh?
Oh, opposite.
Circle. That's a circle. That's a circle. That's a ring.
It's a donut.
It's a donut.
It's a donut. Yeah.
but it's not 3-dimensional like a donut. It's flat.
It's a flat donut. It's a washer.
No comprendo.
So is this.
Play-Doh.
A washer is frequently what people will call it. You have an outer diameter or an outer radius and an inner radius or an inner diameter. So to find the area of the annulus, which is this part out here, and yes, there is a reason that it sounds like anus. The words are related to one another. It's pi big R squared minus pi little r squared.
I think you killed Lily.
Little r. Big R.
Can you erase the diagram?
Yes.
We need to make it out of Play-Doh. Let's see if Play-Doh helps.
So, yes?
Can you please draw the equilateral triangle?
Yeah, an equilateral triangle is just
I do remember that.
Was it good?
a triangle where all 3 sides are the same length.
Oh, okay.
So, in English, anytime you see EQUI at the beginning, that means equal.
Yeah, I know. I know now.
And lateral means side.
Thank you.
So it literally means equal side.
Gotcha.
Okay? All right. So let's take a look at this. The base of a solid is the region R enclosed by the graphs of y equals 2 sine x and y equals x in the first quadrant. Basically, although you don't need to imagine this whole thing in 3 dimensions, think of that as like the base of a building. It's the footprint. Okay? So we're going to draw that first. It's in the first quadrant. 2 times sine of x is just going to be twice as high as sine of x. And y equals x, just a nice 45-degree angle line.
Is what quadrant it's in super important or something?
In this case, yes, because if you didn't restrict it to that, there would be another part in the third quadrant. So this is the base of my three-dimensional figure.
I need
Okay.
Play-Doh.
Pardon?
I said I need Play-Doh. Why is it three-dimensional?
It's the base.
So
That's not
you're looking at a floor plan.
Oh,
This is the floor plan of the building.
okay,
It looks like this.
okay.
Okay? Then it says each cross-section cut perpendicular to the x-axis is a square. So if we were to slice this way, this would be one part of a square. What part of the square would it be? It would be a side of the square.
Okay.
Yeah, it's not a trick question. So we'll start with just the area formula for a square. It's s squared. Then we want the area formula in terms of x. So s is the distance from the upper curve to the lower curve. Well, the upper curve is y is equal to 2 sine of x. And the lower curve is y is equal to x. So that means s is just upper curve minus lower curve. So the area in terms of x is going to be 2 sine of x minus x quantity squared. Pardon me. So now we've got the area in terms of x. Then the volume will just be the integral of this from wherever they start intersecting to wherever they stop intersecting. So the volume will be the integral of this area, 2 sine of x minus x, quantity squared, dx. Pretty easy to see that they intersect at 0. Not quite so easy to see where they intersect over here. So let's grab a calculator and do that. So I want 2 sine of x and y equals x. And again, you can see the part in the third quadrant now. So seeing where these intersect, first curve, second curve, I'm going to guess it's close to 2. .895 yada yada yada. So I'm going to store that value. You don't have to store it, but this way, just in case you move something on the graph and it drops that x value, you don't have to think about it. So then the volume is going to be the integral from 0 to a of parentheses, my first function, which I put in y1, minus my second function, which I put in y2, squared with respect to x. So the volume is 0.456. Yes?
Where is the s squared? Why is the a equal to s squared?
look back at your formulas. For square, it says area is equal to side squared.
But that is not a square.
That's one part of the square. We're not going to have the whole square. So basically what's happening at this point is, I don't have anything that's square that's lying around, but what you would see if you were slicing it, the building is coming up at you, right? This is like the floor plan of a building. And the slice, which goes perpendicular to the x-axis, is going to be a square. So you're going to have this, you're going to have it coming out at you, back over, and then back in. So every slice is going to be a square. You're welcome. So it's always about figuring out, well, what part of my slice is on the base of the building? Okay? You're welcome. And it can be any kind of a slice. All right. And this is one that we couldn't really do by hand because anytime you've got a trig function with a polynomial, it's almost always one where you're going to need a calculator for those. All right, let's talk about volumes of revolution. So here, the region between the graph of y equals 2 plus x cosine x, and that's one of those ones where I'm like, I have zero idea what that looks like, and the line y equals -1 is revolved about the line y equals -1 over the interval from -2 to 2 to generate a solid. Find the volume of the solid. All right, well, let's start by graphing this. So 2 plus x cosine x. And what was the other curve? No, the other curve was y equals -1. And I only need the part from x is -2 to 2. So I'll go -2 to 2. And see, that's x2 plus x cosine x. I don't know how big that's going to be. I'll go -5 to 5, just as a guess. Okay. So now on this one, we're going to take this region, so everything between here and here, and we're going to spin it around. Specifically, we're going to spin it around the line y equals -1. So I actually, even though I'm doing this on a calculator, I actually draw this on the paper because it helps me see exactly what's going on. Oops. Thought I'd had it on straight. So from -2 to 2, and it doesn't matter that you get it exact at all. So this is y equals, what was it, x plus 2 cosine x? Pardon? 2 plus x cosine x. Thank you. I had all the right things, just not in the right spot. And then I've got the line y equals -1 down here. And we're going to rotate this whole figure around the line y equals -1. So we're going to spin it around that. Okay, and again, you don't have to be able to imagine what that looks like in 3 dimensions, but just sort of think about it this way. If I took this piece of index card and I have it like this and I spin it around, it's going to sweep out a 3-dimensional region, right? The difference is that the index card is straight across the top. This is curved across the top, okay? Now, if I take just any representative slice, so if I was to slice it right through here. So now, instead of trying to imagine the whole 3-dimensional things, you just have like this pen is attached on the bottom to this point, and it's rotating all the way around, right? When it rotates all the way around, if you looked at it this way, what would you see?
A clock.
Circle.
It would sweep out an entire circle. Okay? So, and the pen, what part of the circle is that? The pen,
The radius.
it's the radius, right?
Yeah.
So this is the radius of the circle. And now it's really just like the volumes by slicing. A lot of people teach volumes by slicing and volumes of revolution like they're 2 entirely different things. They're really not. What are we going to get when we rotate this all the way around? We get a circle. So the area is pi r squared. The area in terms of x, well, the radius is going to be the upper curve minus the lower curve, so that'll be 2 plus x cosine x minus -1 squared times pi. So I'll simplify that a little bit. That's going to be pi times 3 plus x cosine x quantity squared. So now to find the volume, we'll take the integral of the area times dx. And we're starting our slices at x is -2, and we're stopping at x is equal to +2. So let's see, Math 9, from -2 to 2. Oh. I can retype it, or I can go, yeah, it was the first function minus the second function. It's about the same number of button pushes. It's 44.316. I'm sorry?
You said the wrong interval.
Oh, where did I get 5 from? Thank you. Stop it. That's better. 36.687. Everybody good on that? All right, one more example today. So for this one, the region in the first quadrant, enclosed by the graphs of y equals cosine x, y equals sine of x, and x equals 0, is revolved around the line y equals 2 to form a solid. Find its volume. All right, so we just need the part in the first quadrant. And I've got y equals cosine x, which looks kind of like that. Y equals sine x, which looks kind of like that. And what is x equals 0? It's the y-axis. This is the enclosed region. And then we're going to revolve that around the line y equals 2, which is way the heck up here. So again, if I take a representative slice of this from here to here, you do have to do a little bit of imagining at this point. So I've got this little stick, and I'm revolving it around this line that's way up here. What kind of a thing am I going to sweep out now? It's not going to be a circle any longer.
I can only think of the bad word.
The annulus.
Yeah, that one.
Because this is no longer attached to this point. So when you sweep it out, there's a gap between the two all the time. So the area for this is going to be the area of an annulus. It would be pi times big R squared minus pi times little r squared. The big radius is going to be the distance from the center all the way out to the outer edge, which was y is equal to sine of x. So big R is going to be 2 minus sine of x. And then the little radius will be the distance from here to the other curve, y is equal to cosine x. So that'll be 2 minus cosine x. So the volume is the integral from 0 to pi over 4, because that's where those intersect, of pi times 2 minus sine of x quantity squared minus pi times 2 minus cosine x quantity squared. Sorry for going a little long.